Okay, well, I'm going to start. So my name is James Roper. I work for Lightbend. I've been working primarily on Lagom and before that Play Framework. And today we're going to be talking about CRUD and event sourcing. So you've all got a great introduction at a very high level to what event sourcing is from Jonas yesterday. But today you'll get to see an implementation of event sourcing and hopefully a much more practical grounding to the stuff that he's been talking about. So what we're going to do today first is we're going to failure test some CRUD solutions. We're going to look at, okay, if we're using CRUD, what can go wrong, and try to solve that a bit and work and see what some of the problems are. We're going to learn about event sourcing in a much more, you'll actually see it being written. We're going to see why event sourcing is resilient in comparison to CRUD. And we're going to do some live coding. So Lagom is a microservices framework that Lightbend has developed. It builds on top of Akka and Play Framework and offers some abstractions there to help you. And you'll see just how event sourcing works there. This demonstration is going to be in Scala, but the concepts translate to any language. And I should say that there's nothing really specific to Lagom in this presentation, but I do want to show something practical, so I have to choose an implementation. And of course, as a maintainer of the Lagom framework, I'm going to choose Lagom. So I've written an application. It's a holiday rentals application, pretty much like Airbnb. It's going to take over the world. It's going to be much better than Airbnb. Doesn't quite have the feature set yet, but you just wait. So I went to my presentation last year at Reactive Summit, and I learnt that using a synchronous architecture where services are making synchronous calls on each other using REST can cause big problems. So I've implemented it as an asynchronous architecture. And if you're interested in learning more about why I've used an asynchronous architecture, you could probably watch my presentation from last year, or I'm sure there's plenty of other presentations here this year that are going to talk about similar things. I'm using Kafka for messaging, but I've written my reservation service, so this is the thing that actually tracks what listings have reservations on what dates. I've written it using CRUD. In this case, well, we can pretend it's using Postgres or Oracle or something. In this case, it's actually using H2, but I'm using Slick on top of that, so it kind of abstracts away from which database implementation. But it's a CRUD relational data store. So let's take a look. So this is it. I'll actually go back to search, so I can search for all the listings available between the 19th and the 26th of October. And here are 4 listings, a villa, some things by the beach, a B&B. And so I can view the current reservations. There's actually no reservations for this beach house. So how do I go back when I'm in full screen mode? We'll do that. So I'll go back and I can click book. So I've now booked that listing. Probably the final version might have a bit more than that. You probably have to enter a credit card or something like that. But for now, just a minimal viable product. It's pretty cool. And final version will probably have more of a calendar here showing when it's not available, but you can see here, well, that booking is now there. It's reserved from the 19th to the 26th. Probably also be good if I could log on. If I go back to this page now, the booking no longer shows because it's not available. The listing no longer shows because it's not available on those dates. I could go back and search for other dates and it will come up. So the architecture of this system. I've only got two services so far. There is the reservation service, which makes the bookings, as I said, and the search service, which I use to search for reservations on a particular date. As I said, the reservation service uses a relational database store. The search service uses Elasticsearch. Well, it will. Right now, it's actually just storing in memory and persisting JSON to the file system, but, you know, MVP and all that. And then they talk to each other through Kafka. And so we've got this event at the moment when the reservation service makes a booking, it emits this reservation added event that gets transmitted over Kafka, and the search service consumes that, updates its search index so that now it won't return reservations for that listing on those dates. So the basic approach for my reservation service, when I get a booking, I want to update the database. So my reservation service needs to know what the reservations are. And I want to publish to Kafka. So I want to do these two things whenever I receive a reservation: update the database and publish to Kafka. So here's my approach. This is what I've implemented now. I've got my services database and Kafka. I hope that's readable, but I'll explain it anyway. I begin a transaction on the database. I then do my update. I actually do a select first to make sure that there's nothing reserved for that date already, but the end result is that I do an update or an insert to put my reservation in the database. Then I commit it, and then I publish to Kafka. So, what happens if something goes wrong? Let's just say that Kafka goes down. So I'm going to simulate that. This is my configuration for Kafka. I'm going to simulate that by actually changing the port for Kafka, so it's no longer going to be able to connect. Now Lagom implements hot reload, so as soon as I change that, you can see it's reloaded the reservation service. And so now I'm going to try and book this villa by the water. And it's taken its time, waiting. Well, of course, it's not going to work because Kafka is down. Okay, well, Kafka comes back up. And that should reload. Did that already reload? Did that save? Ah, that already reloaded. And so I go back here. I click Book Now. Well, of course, the reservation was saved to the database, so I can't book it again. Oh, actually, no, that's saying that it hasn't reloaded yet. Have we reloaded? Book Now. Oh, it hasn't reloaded. It's taken its time to reload. There we go. So now I can book now. Listing is already booked for those dates. MVP, I'll improve that error message. I can see the listing there. So there's my listing that I booked before. But on this page, it's still showing it as available. So I've got this problem now. So the question is, what if the service goes down during the transaction? Or what if the database goes down during the transaction? Or what if Kafka goes down during the transaction? Or what if the network goes down during the transaction? All of these things can happen for whatever reason, and especially if you're running on the cloud, these things, you do see them happen all the time. And so if Kafka went down after we've committed our transaction, or the network, or the service that's orchestrating this, then that publish doesn't happen. And so now we're in this state where we're kind of in this terminally inconsistent state. The search service goes and says, you go and ask the search service, can I see the listings for this date? And it goes, oh yes, here you go, here's the listings. But then when you go to book it, the reservation service comes back and says, no, already got a booking there. And the search service is like, well, why didn't you tell me? I tried to, but Kafka was down. And really what the essence of the problem is I had those two things that I had to do, update the database and publish to Kafka. I needed them to either both happen or not happen. I needed them to be done atomically, and they weren't done atomically. Maybe we could kind of change our code a bit and come up with another solution. So we're using transactions. We begin our transaction, we do our update, then we publish to Kafka. And so if Kafka's down, or if the network's down in between the service and Kafka, that's going to cause us to not commit the transaction, so we'll be fine. I mean, I can change the code to do that. So we've got reservation service implementation. So here's the thing where it's publishing that event after it's done the add reservation on the DAO. We get rid of that publish, we don't need that. And instead, in the DAO, we're going to do a publish just there, and that's going to solve the problem for us, right? Well, no, we've just kind of moved the problem, because if the commit then fails, if the database goes down or the service goes down, the network goes down before we do that commit, but after we've done the publish, well then now the search service knows, is going to think that there's a reservation then when there is none. And that's probably even worse, because now, now this listing, whoever listed it, is going to lose money because nobody can make a reservation then because they can't find the listing. This thing can be generalized as something called the two generals problem. So you may have come across the two generals problem before. For those that haven't, I'll explain it. We've got two generals. The two generals want to attack a city. If one general attacks the city will overwhelm them and they'll lose. But if they both attack at the same time, they can overwhelm the city and win. So they need to both attack at the same time. But they're on opposite sides of the city, and the only way that they can communicate with each other is to send messengers around the city. Now the problem is the city has patrols that are in the countryside and is able to intercept those messengers sometimes. So the generals can't rely on the messengers getting through. But they need to both decide at what time and have consensus as to when they're going to attack so that they can be successful. So if our first general sends a message to the other general saying, attack at noon, the other general might receive it, but the first general doesn't know if he received it or not. And so the first general wants to get an acknowledgement back from the second general so that he can know if that it's been decided and they can attack. So the second general sends the acknowledgement. But that acknowledgement might not arrive. And if it doesn't arrive, then the first general is not going to attack. So then how does the second general then know that he should attack? Well, he needs an acknowledgement to the acknowledgement. And you can see, going back and forth, there's going to need to be an infinite number of acknowledgements in order for these generals to come to a consensus, which is impossible. So it's been proven to be unsolvable. You can kind of imagine it there, but this problem applied to distributed computing, where you have two different systems and an unreliable communication mechanism trying to communicate with each other, it is impossible for them to reach a consensus. Well, but what about two-phase commit? So can't we just use two-phase commit to ensure that we've transactions on both parts of the system either get committed or don't? Well, two-phase commit is not some sort of magic fairy dust that can get around the two generals problem. The two generals problem has been proven to be unsolvable, and so there's no way that two-phase commit can guarantee that two systems agree on the same thing at the same time. What two-phase commit does do is it just reduces that window in which a failure can cause a problem. So two-phase commit basically says, goes to all the systems, say, please get ready to commit. Do anything that's going to be expensive now, and then hold, and then when I want you to actually commit, commit. And so the idea is that in that moment when you do the actual commit, it's maybe a millisecond or something. You've got this very small window that everything has to be up for, and hopefully everything works. Now, of course, whenever you say hopefully, what happens when everything is going wrong? So for example, my system is overloaded. So if my system is overloaded, if it's been overwhelmed with requests, buffers are probably going to fill up, I'm probably going to start getting out of memory errors, network starts dropping packets, it's actually the time when I'm most likely to get a failure. But also what happens during that time? Everything slows down. You tell something to do the actual commit, and that window is actually much larger because it takes a lot longer to do it. So two-phase commit helps you in the happy case, but really when we're talking about consistency, we don't care about the happy case because the happy case is going to work without two-phase commit. We care about the case where things are going wrong. Is my data going to be consistent? And in that case, where failure is most likely to happen, two-phase commit is also most likely to fail. And the other thing about two-phase commit is that it comes at a very high cost. So you're saying, when you do a two-phase commit transaction, you're telling the database, hey, can you please hold and wait for this to happen for me to tell you commit again? And usually that holding requires some sort of, okay, I'm going to hold, I'm not going to do anything else for this time because I don't want anyone to see the results of this transaction so that it can be done atomically. And so you've got this kind of coordination that has to happen between your cluster, which slows everything down and you end up doing things one at a time in an area that needs to be concurrent. So two-phase commit doesn't really work. Maybe it's just too hard. And let's be real about this. Not all problems need to be solved. There are trade-offs. And maybe we can accept a little bit of inconsistency if our implementation ends up being not too complex. And I guess the answer to that is, in some cases, it's fine to live with the inconsistency. But what if there is a simple way where it's not too hard, where just by changing our approach a little bit, we can actually get a guaranteed consistency and not have to deal with the inconsistency at all. We can't solve the two generals problem, okay? That's unsolvable. But what if the two generals came up with a different plan of attack that didn't require them to have consensus? Now, I don't want to stretch the two generals analogy too far, but for example, what if one general didn't attack, but instead approached and besieged the city and dug in? So he could probably do that for a number of days. And then once he's there, he could send messages to the other general saying, hey, I'm dug in, I'm sieging the city. If you come, then I'll see you and we can both attack. So that's an example of, in that specific problem, how we might come up with a different plan of attack. And in microservices, we can also come up with similar different plans of attacks. So this is where we come to event sourcing. So you've all heard Jonas's presentation. Event sourcing means you don't store the current state. Instead, you just store the events that occurred, and then you work out what the state is from the events. So when you need to make a decision and you need that state, you compute the state from the events. And so then when we go and implement this is what it looks like. We have our service in our database in Kafka. And when we add a reservation, we do an append on the service, on the database. Now, I've called this operation append because there doesn't need to be a transaction here. It's just one operation on the database. It's just an append, and that actually greatly opens up your options as to what you can use for a database. And then after you've done the append on the database, you're done. There's nothing more to do. You've done your operation. What about Kafka? Well, we'll get to that. Let's just have a look at how this is actually implemented. So Lagom has a concept of a persistent entity. This is also known as an aggregate in the terminology used yesterday evening. And it's a unit of persistence. It's usually something that you have, in this case, it's the reservation. So there's lots of different entities, all with the same kind of structure, but actually representing different things. And the first thing I'm going to do here is define the events. So we have this a sealed trait. If you're a Java developer, that's just an interface called a reservation event. It has this tag on it. We'll learn about what that is for later. And I'm going to, for today, just implement one event, the reservation added event. So here's our reservation added, has a listing ID, it's got an ID for itself, for this reservation, and then the details of the reservation, we can see there it's got a check-in date and a check-out date. Down here in the companion object for the reservation added, we've got a JSON format. We need that, so Lagom will serialize your events and store them in the journal. You need to define how that serialization happens. If you're familiar with play.json, this is just a play.json format, so this is going to be serialized to JSON and stored in the database. So there's our event. We'd probably, in the next versions, define more events, so reservation cancelled, listing delisted, and things like that. But for now, we've just got one event. We now need to define the commands. So the events are the things that are emitted that happened in the past. The commands are the imperative things that request things to happen now. So like events, we define a trait that all the commands will extend. And then I've got one command to add a reservation. And it's got a reply type. It's going to return the reservation added event that it just added. And I've got another command to get the current reservations, which is a convenience at the moment to get the reservations directly from the entity. In future, I might actually separate that out and do a proper read side where I can query from. So I've got my events and my command, my event and my commands. I also need to have some state. So here's my reservation state. It just has a sequence of reservations. So all the reservations for this particular entity are stored in that state. And so that's the thing that's kind of temporary and is built from the events. And I've got this serializer registry. That's more of an implementation detail where I tell Lagom where all my serializers for my events and commands are. Not too worried about that right now. So now I need to define some behavior. So this is a Lagom class, persistent entity. I declare my reservation entity as a persistent entity. I tell it the type of my command, my event, and my state. Here I'm just parsing the listing ID from the string entity ID. I declare an initial state, which is the empty reservation state, no reservations. And I need to declare the behavior. So the behavior is how do we respond to commands that are coming in and how do we respond to events that are replayed. So you could have different behaviors for different states. This entity doesn't really look like a state machine where you've got but perhaps if I had supported delisting, then I might go into a delisted state where I rejected all reservations, so I'd declare a different behaviour for that. But for this, I'm just handling this one reservation state. That's my state. And now I define all the behaviour in these actions. So this is a command handler. So when I get an add reservation command, I'm going to do some validation. So you can see I'm checking that the checkout date isn't before the check-in date, that the check-in date isn't before now, and also checking that the reservation doesn't conflict with an existing reservation. So, and in each of those cases, I will fail with a bad request if that happens. But if the reservation passes, then I'm going to persist an event. So I'll persist a reservation added event, and when that's done, I reply with that reservation added event. So that's handling the add reservation command. I also want to handle the get reservations command. Very simple. It's just replying with all the current reservations, dropping all the reservations that are before now. Now I've handled both of my commands. I also need to handle my events when they get replayed. So I'll add an event handler for the reservation added event. And so when I replay a reservation added, I return the new state that has the reservation added to the current reservations, and I ensure that it's sorted by date. And so that's my persistent entity. I need to wire that in just a little bit. So I register my reservation entity with logom. Now logom actually shards your entities across a whole cluster, so you need to do this reservation so that it can start up that sharding. And I'm just going to configure my serializer registry for my reservation JSON serializers. Okay, so the entity's there. I now need to rewrite my service to actually use the persistent entity. So the first thing is I'm going to write this helper method just to look up the reference for the entity. So this gives you a reference based on an entity ID that you can then go and send commands to. Then here's my reserve method. This is a logom service interface, and this is the way you implement service calls, which are REST calls. And so I'll reserve it. I get my reservation entity reference. I then ask it with the add reservation command. So a command may fail, which is why it's an ask or a request. You can't force it to do what you want it to do. And then when I get the reply, I map it to this API representation of the reservation added. So this is the reservation added persistent event that's coming back. This is what you call a anti-corruption layer. So those events can evolve in their structure, and because I'm doing this translation here to an external representation, they can be independent of each other. And so there I'm done with the reservation, and I'll just implement get current reservations as well, which is very simple. Okay, so that should recompile and reload. Started. Let's go back to our holiday listings app. I'll book this budget hotel, and it's booked. We can see it's storing the reservation, so that's all good. And of course, it's still appearing there in the search results. Why we haven't published to Kafka? So, how do we publish to Kafka? We don't need to do anything else when we handle that reservation command. That's done. That's the whole point. We're not doing two operations anymore. There's no do this and do this. So there's no need for an atomic operation. Instead, once that's done, we have something in the background that publishes the messages. Now each event in the event log has an offset. And what we do when we publish the messages is we store that offset to the database. So when my service starts up, it's going to go to the database and select the last offset that it published, so find out where it's up to. Having got that, it can then start a stream from the database. Now how this looks like depends on your back-end implementation. Using the JDBC here, it's actually Lagom implements a polling where it keeps polling for new events since the last one that it published. But we do that, but effectively from your point of view as a developer, it's a stream. And so then this happens when the service starts. At some point in future, you're going to receive an event. Okay, so that reservation added event is going to be given to you, and then you can publish it to Kafka. And having published it to Kafka, you can then update that offset table so that you can restart from that place later. So we can have a look at implementing this. So in Lagom, in a service, you can declare a topic. We've declared this reservation events topic. I'll put that on this line. So this topic produces a tagged stream with offset. So I can tag my events with multiple tags to shard them and then do the publishing on multiple nodes. I've only got one tag in this case. That's that tag that you saw that I created before. So it's just going to, it ensures that it's only going to do this publishing from one node. Lagom assumes that you could deploy in a cluster, but if you're going to publish events and reading them from a stream, you want to make sure that each member of the cluster isn't doing the same thing. So having, Lagom will then do that read offset, so it handles that offset for you, and it gives me the tag and the offset, and now I can start the stream. So I go to the persistent entity registry, and I get the stream for that tag and offset. I then map it, so I get these event stream elements, which have the current offset for this element, as well as the event itself. And I convert it into the reservation added representation for the external API that gets published, along with the offset. And so that then gets, Lagom's infrastructure consumes that and will track that offset and persist that offset so that when my service crashes, it will ask to get all the events since the last offset. And so having implemented that, wait for that to restart. And so now the listing disappeared. Now I didn't redo that operation. I didn't try and book it again. I had a problem before because, let's say I forgot to publish this event, but somehow the search service has found out about it. And this is the thing, because the actual taking the reservation is not in any way connected to the publishing, if something's wrong, like it wasn't even implemented, can self-heal. It can start from the start, or from wherever it was, in this case it's from the start, and publish these events across. And so whether there's a failure, whether there was a requirement that wasn't implemented, if I have a new requirement in future, I can ensure that my system will come up to date. Now try to doing that with a CRUD system. You've just got this is the current state. What does the system that I'm talking to know about or not? We don't know. And of course, it should be working in real time as well, so I can book that and it disappears, search service knows about it. So this is resilient because, well, if at any point in that fails, like let's say the publish fails, well, we didn't persist the offset, so when we restart, we'll start from that offset that we didn't persist. Or maybe if the publish succeeds, but we don't update the offset, well, the worst thing that happens then is we just republish the same event. And so the important thing, my search service does need to be idempotent, but of course, Kafka messaging is at least once anyway, so we're not making things any worse to what the guarantees that you're getting are. So the advantages of event sourcing here. So Jonas has already talked about a lot of advantages, but some of these they might be a bit more clearer with a concrete implementation. So obviously we have a fact-centric approach. Okay, we're sending facts across the wire. We don't need to worry about any, what do you know about them and what part of my state, is this state stale? We just are sending facts. And because we're doing this, it means it self-heals when problems occur. Now, it's not all magic, but you can see, with that, you get this kind of, like with transactions on a relational database in a monolith, where everything either happens or it doesn't, and it's kind of magic and you can trust that. Here we get this case where if something doesn't happen, you can go back through history and replace it and replay it, which gives you these self-healing capabilities. Obviously, we have the built-in audit log. So if I implement cancelling reservations in a relational data store, I actually have to destroy that data, the data that the reservation is there, and then there's no record that there was ever a reservation. Whereas in event sourcing, you have a reservation added and a reservation cancelled event for all of time, and so you know that you've got this audit log. And of course, we can compute the state of the system at any time. So if there was a problem, like let's say I end up with 2 people that reserve the same place at the same time due to a bug in my system, I want to work out, well, how did that happen? Well, I can go and I can bring up my reservation entity up until the point that the second person tried to do the reservation, and then I can send that command again and say, oh, okay, we had a problem in my validation logic and it allowed the reservation to happen. So there's some details to the event sourcing here that if you haven't come across event sourcing before, you might have some questions. So I'm going to try and predict some of those or address some of those questions before they come up. And the first is, how is consistency addressed? So if I'm having to, in a relational database, I just do a transaction and it handles, if you've got 10 concurrent things trying to access that same data. It somehow sorts it out and maybe causes some transactions to fail or blocks some transactions while this one continues. In event sourcing, how does that work? Because you've got to load all the events, do something, persist a new event. What if something happens at the same time as that? And the answer is, in Lagom, each entity only runs on one machine and only processes messages one at a time with one thread. And the way that is managed is Lagom is built on Akka, which has this cluster sharding feature. And so your entities are divided into shards. And so when a command comes in, and if the entity doesn't live on the node that received this command, it will go and make that. It will go and send the command to the node that it actually lives on and do it there. And there, it's an actor, it's got a mailbox, and these things are handled one at a time. What about replaying events? Isn't that expensive? Every time I need to do something, I need to load all these events from the database, which could potentially be very long. Maybe there's thousands, even millions of events for a single entity. And I need to replay them all and compute my state so that I can then do one more thing. So Lagom and every event source implementation usually supports something called snapshots. And what this is, in Lagom specifically, configurable every 100 events the state, the current state, is snapshotted and persisted to the database. Now that snapshot should just be considered a cache. We could delete it at any time because we've still got the events, but it's there. And so then whenever we load an entity, first we check the snapshots table. Is there a snapshot for this entity? If so, yes, load that. And also read what offset were you up to when you did that snapshot. And so then when we replay the events, we start from the offset that, the next offset after that and replay any events that weren't included in that snapshot. And so with a default of 100 events, you can ensure that you're never replaying more than 100 events. And if your events are fairly small, loading 100 events from the database is quite efficient. But sometimes people have complex state calculations, and so they make it much shorter. The other thing to realize is that these entities are stored in memory. So in Lagom, they're persisted after about 2 minutes, they're passivated after 2 minutes, but if you get a command in for an entity, for the next 2 minutes, if another one comes in, it will use the same state that's in memory. And this is really a nice feature because you get this very strongly consistent in-memory caching where compared to a relational database, if you do use an in-memory cache, what happens when you've got multiple nodes? You need to start using coordination and other technology there that kind of, often you'll lose some level of consistency with that, but with event sourcing, because you're guaranteed to only be handling these events on one node, one at a time, this cache in memory is actually strongly consistent. What about querying data? So you can read the entity state for a single entity, but what if, let's say, we wanted to get all the reservations for this one person? Then you need multiple entities, and we don't have any index there because all the events are just stored as JSON in a log table. We don't have an index to be able to say, give me all the events give me all the listings for this person. The answer there, of course, is CQRS. And so the search service is a perfect example of this. We implemented the search service using Elasticsearch because that's the right tool for the job. But it's actually the tool for all, doing that pattern is the tool for all querying when you do an event sourcing. So in that case, the events are shipped to Elasticsearch and we store it in a format that is suitable for my queries. Lagom also supports local read sides where you can, instead of sending it through Kafka, just consume the event stream directly and update some local tables which might be involved in some validation or something like that. So, in summary, we've learnt that CRUD is not an ideal fit for distributed systems. Now, I'm not saying that you should not use CRUD in distributed systems. I'm not saying that relational databases don't have a place in distributed systems. There are plenty of places where CRUD is ideal. But for many cases, and I would say for the go-to, the default case, because of this issue where keeping things in sync is really difficult, storing the current state is not a good fit. Instead, an event-based approach, like event sourcing, is an ideal fit. It's the go-to. Well, what if you don't really have an opinion, you just have this service, what are we going to use to store it? Let's use event sourcing as the first step. Or maybe event sourcing doesn't work for this particular niche use case. Okay, well now we can consider using something else. But the kind of, definitely at Lightbend, we recommend in microservices the go-to for persistence is event sourcing. And we've seen that event sourcing brings a host of other advantages. So next, you can check out Lagom Framework, www.lagomframework.com. There's a number of introductions there. We've got a sample app called Online Auction, which is basically a clone of eBay that shows event sourcing there. And this presentation itself you can get from github.com/jroper/crud2es. It's got the presentation itself. It's also got in branches the code in both the state at the start and the finished state, so that you can run through and look through the code and the changes that I've made yourself. So thank you for listening. I think we have time for a few questions, so there's a microphone in the middle if you want to ask a question.
So what's the advantage of this over a system like Martin Klubman had a thing called bottled water that basically takes the database log directly and copies that to Kafka?
So I'm getting the sound back. What's the advantages against what?
A system that uses the database's log.
Yep.
To copy that into Kafka rather than having that.
Okay, so the problems are not unsolvable with a CRUD solution. Certainly using the database log is a way to solve it, and if you really wanted to use CRUD, like if you've got something that's just perfect for CRUD, often a solution would be to maintain your own log in the database of messages so that you can update that in the same transaction. The advantage of this, so first of all, working out the intent of an update reading from the database log is very difficult. So was this, maybe for a reservation it's not too difficult, but why was this change done? What event should be created from that? And that's often a very difficult question to answer. But it certainly is an alternative solution. It's just, it requires a bit of thought, and sometimes it doesn't work so well because you don't know the intent to know what event to publish.
Great talk, James. I really enjoyed it. So in your application, when you actually looked up whether the reservation had been made already,
yep.
There's certainly, it's eventually consistent. So two people could have made the reservation at exactly the same time. So that's seems to be a really common pattern with the event sourcing. Do you have a pattern for how would you deal with that?
Okay, so first of all, the most important thing is that we ensure that two reservations aren't made at the same time, that they don't actually be made. And that was solved there because it's done inside the persistent entity. And the persistent entity it knows what the current state is. So when it gets a command in, they're going to come in order. So you'll get one, if two people make it at the same time, it doesn't actually happen at the same time. One command goes in the queue, next command goes in the queue. They get processed one at a time, the second one will be rejected. So the actual ensure that no two reservations happen at the same time, that's solved. But what about the problem of, well, if two users are doing a search at the same time and click at the same time, what? And that problem exists just as much for CRUD, because you do a search and you get a web page, you can keep that web page open for 3 days and then click book, and you're not going to, and obviously somebody might have booked it in the meantime. And it's really how to solve that. That's part of, the real world is eventually consistent. So to solve that is a business problem. Maybe when we return search results, which you often see this in ticket booking systems where you want to book a particular seat, we put a hold on that particular seat. And so we don't return the result until we've got a hold, and then the user has 15 minutes to complete the transaction, and you often see the countdown. But that's a domain problem that's not really specific to event sourcing or CRUD. But yeah, you do get the actual, let's ensure that our data is not consistent from events, is not inconsistent.
Great, thanks.
Yep.
Hi, James. Great talk indeed. I have a question. I'm not sure if it's related to the first question that was asked. What happens in the new system if the database goes down? I mean, Kafka will eventually catch up, but in the interim, wouldn't the listings page still show incorrect information? That's
correct. So at the end of the day, we're going to have outages, and we'll try and use, the default database for Largom is Cassandra, which is highly available, but you will still get outages. And there's nothing, we can manage that, but there's nothing that we can, like failure happens. If the search results are showing, if the database has gone down, you're not publishing the events, the search results show something out of date. So that's a problem, but then if you go to book it, the database isn't going to be able to handle it anyway because it's down. So, that's a problem, but I don't think it's a problem that's, sorry, that's specific to event sourcing or CRUD. You address that by using a more highly available database where parts can go down and using replication and things so that these failures don't impact you as much as possible.
Are there any scenarios or instances where you do not advocate using event sourcing?
Yep. So if, let's say I have a sensor that's sending temperature data every few milliseconds in a manufacturing system, I probably am not interested in storing that data, all those events. So very highly frequently updated things. That said, there's a lot of cases where you would think maybe you wouldn't want to serve events, but store the events, but it's actually very useful. We see people doing logistics systems where trucks are sending GPS updates every 10 seconds, and they store all those events. And it's a lot of data, but it gives them an incredible amount of power when they can go back and see and look at where their trucks went and be able to work out more efficient routes and things like that. So yeah, the frequently updating is an example. If you have data that's better represented as a graph, then maybe you'll use a graph database. And often a pattern might be, well, I've got some strongly consistent stuff on kind of an entity type of thing that I'll put in front of, and so I'll use event sourcing in front of that, and then the events will update the graph database to do that more, to do that other processing. And then there's also non-technical reasons. We've got a legacy Oracle database and we really need to keep on using it. Maybe you might use that in the interim and use this a manual message log in the database that then gets published.
So really great talk on the pros and cons of write-aside and the dangers of two-phase commit versus write-through, yep. and the reliance on that. I really like that. If you can put up your slide back on that one sequence diagram where you're first writing and you're doing the append and then the Kafka's off. So I think just a previous question you answered that your persistent store is Cassandra. Is that correct? It's one of the ones that you kind of recommend. I know
Was it this one or this one?
Yeah, it's one of the ones that you kind of recommend. But when you the previous one, that one. So this one, it could be any database, but basically the emphasis of this slide is that it's an append paradigm. Is that correct?
Yep.
Okay. That database column, that looks a lot like a log.
Yep. So Largom's persistence backend is built on Akka persistence, which is pluggable. There is a Kafka implementation of it. There's some limitations to the Kafka because Akka persistence gives you a lot more power than just a log, and so you don't get the full feature set if you're using Kafka. But yeah, it is, and we use, like we said, Cassandra is the default. Cassandra may look like a key store, but it's an append-only database. That's how it stores stuff.
Thank you. You said the key thing, a key store. Yep. Thank you.
Okay, if there's any more questions, come up and ask me. Otherwise, go and enjoy lunch. Yep.